Hey guys, today we are going to learn about how to organize quantitative data. So yesterday we talked about how to do qualitative data. Qualitative, remember, is like a category, so it has a name. Today we're going to talk about the quantitative data. So typically these are more like numbers that we're going to be organizing here, and there's several different ways we can do that. So the first step when we're working with quantitative data is we have to decide if they're discrete or continuous. So we defined those in the first chapter. Remember, discrete means they are like distinct numbers, countable numbers. How many kids do you have? Okay, it has to be 0, 1, 2, 3. Whereas continuous could take on any value. So that would be more like, what is your income? That could take on any value. So what we're going to do then is we're going to cut them into classes, which kind of create categories in this data. So yesterday our data was categorical or qualitative. It already had categories. So when we have quantitative data, we're going to take this quantitative data and we're going to break it down into classes, which kind of put it into categories then. So here's some raw data. Remember, raw data means nothing has been done with it, just like raw chicken hasn't been cooked yet. So this data says represent the number of available cars in a household based on a random sample of 50 households. So how many cars do you have at your house? What we want to do is construct a frequency distribution. So yesterday we looked at frequency distributions as well. So we're going to do that same thing here, but this time it is for qualitative or for quantitative data. Yesterday for the qualitative. So just like yesterday, we would want to decide on our classes. For this, it just kind of makes sense to use the numbers 0, 1, 2, 3, 4, 5, since these are discrete data points and relatively small numbers. It's not going from 0 to 150. These people don't have 150 cars available to them. So 0, 1, 2, 3, 4, 5 creates a good number of classes. Choosing classes is a little bit more of an art than a science. There's not like a rule for how many classes you should use, but it's that you want to use enough classes that you're not grouping the data so much that you're only going to end up with like 2 or 3 bars in your histogram, because that's not going to really show anything. Or you don't want to have so many classes that your graph is going to end up just being full of bars and difficult to read and also time consuming. So it's kind of a little bit of an art. You want to think about Goldilocks and have like the just right number of classes. So 0, 1, 2, 3, 4, 5 works well here, and you would look through that and you would tally up each of those. So there's a 3, a 0, a 1, a 2, 1, 1, 1. We're going to tally those all up, figure out how many we have, and we can get our frequency. And then we can, like yesterday, get our relative frequency by dividing by the total number represented in the sample. And then those give us our proportion, which we could then change into percent. So we could say what percent of families have 2 cars available, and that would be 44%. Or we could say what percent of cars have, or of households have 2 or 3 cars available. Then we would add those up, and we would say that'd be 58%. Okay, or what percent of houses have more than 3? Now that can be a tricky question, because more than 3, that's not 3. So that'd only be 4 or 5. So that would be 8%. So then we're going to create a graph with these frequency distributions. And that graph is called a histogram. I already said that word once, but a histogram is basically like a bar graph that we talked about yesterday, where we're going to use rectangles drawn to the height of the frequency or the relative frequency. The width of those rectangles should all be the same. The big difference between a histogram and a bar graph is that in a histogram, the rectangles touch each other. They're right next to each other because that shows that this data is this quantitative data and that we as the researcher created the classes. that they weren't already distinct categories, that we chose those classes. So in a histogram, the bars should touch each other. So we have our frequency here and our relative frequency from that other one, and we would put this into a graph by putting the number on the x-axis, the number of cars, so our classes, the categories that we have created on our x-axis, and then the frequencies on the y-axis. I guess I don't know. It doesn't say here. It was very specific yesterday in our notes. Remember, it said several times that bar graphs could be done either way. I can't ever think of an example where I've seen a histogram done sideways. And it didn't specifically say there whether you can or not, but I believe histograms are at least almost always done with vertical bars, if it might even be a rule that they have to be. We can also do the relative frequency. Notice the shape of the two graphs is exactly the same. It's just the y-axis values changed because we're looking at the relative frequencies or the frequencies. So those classes are how we group up the data. When we have a large number of discrete data values, we can't do every individual one like we just did with those cars. Or if the data set is continuous, then we might be getting a lot of decimals and stuff, so we have to group those somehow, and those groups are called the classes. So the following data represent the number of persons aged 25 to 64 who are currently work disabled. So this has already been classed up. This is not the raw data. This data has already been put into classes, and the classes are those age groups. So 25 to 34, 35 to 44, 45 to 54, and 55 to 64. The lower class limit is the smallest number in there, and the upper class limit is the largest. So in that first one, the lower is 25, and then the upper in that first one is 34. The class width is the difference between, this is important because students always do this wrong. I guess I should say always, often. Students often do this wrong. The class width is the difference between consecutive lower class limits. So the class width on this is 10. What many students want to do is subtract the two values within one class. So for example, 34 minus 25, and then you would get 9. That is incorrect. The class width is found by subtracting consecutive lower limits. Okay, that's because if we're working with continuous data, somebody might be 34.5 years old, right? So it's actually 10 years have passed from the 25 to the 35 before they go into that next age group. So make sure you're subtracting the lower limits to find those class widths, not subtracting a lower and an upper. So here's some raw data. This is the time between eruptions for a random sample of 45 eruptions from Old Faithful. These times are in seconds. So this is our raw data. It's kind of hard to look at, and it doesn't really speak to us at all. You just see a whole lot of numbers. So we want to try to organize this data so that it can speak to somebody and maybe tell some sort of a story. So we need to create a frequency and a relative frequency distribution. So what we would need to do is kind of look at the data and maybe look for our smallest number and our largest number and try to decide on some classes. So the smallest number within there was 672 and the biggest was 738. So we want to think about, well, how many groups are good? And again, there's not a rule to this, but it's kind of more of a Goldilocks thing. If we count by tens, that gives us 7 groups, and that seems pretty manageable to have 7 groups, and counting by tens is kind of nice. So then our class width is 10, and we can encompass all the data that way. So then we would tally that up. That second class ended up empty. That's okay. That's totally fine. We wouldn't want to then adjust the classes necessarily to try to cover that. It's fine to show that that is empty. And then we could create a histogram of that. Now, when we create the histogram again, we would put those, the time between eruptions, our classes on our x-axis and our frequencies on our y-axis. The bars should be touching each other, except for that one case where the bar is kind of invisible because it has a height of 0, but all the other bars would be touching each other, and we would just be missing that one. So again, the choices on the class limits are kind of arbitrary. There's not one right way to do it. And again, they also say it's more like an art than a science here in creating this. And sometimes you might want to create more than one histogram and kind of see which one you feel like displays the data the best. Now in your homework, they're going to be pretty specific about what classes you should use or the class width or where you should start it, just so that your answers are all consistent. But in actual practice of displaying data, you have a lot of choices to make. So this would be a choice as well. So the original counted by tens. This puts them into classes counting by fives, a class with a 5. To me, this is a little more overwhelming. It's as a histogram, we would have a lot of bars, and they're all relatively the same height. There's not a great difference. We see those 7s there in the middle, so we can see that that's most common. But to me, this is a little bit overkill on our number of classes, but it's really a preference thing. So some guidelines, find the smallest observation and then maybe go slightly lower than that. And then for the class width, we want to think about what is the spread of our data. So the biggest minus the smallest would be our spread of our data, and divide that up by how many classes you want to have. And it says generally we should have between 5 and 20. To me, 20 is a bit large. So I would, stick closer to 10-ish as being a good rule of thumb for the number of classes that you might want to have. And then you want your classes to work out to be a nice even value, so you would round that up because likely this could end up in a decimal when you do that division. So you would round that up to determine how big your class width would be. It's also kind of nice if your class width is an easy number to count by. Like in the other ones, it was 5 or 10. That's kind of nice. If it's 7, that's fine. But then you have to think about counting by 7s, which is a little bit trickier. So here is that same data using the class width of 10. So this is that first frequency distribution that we did where we were counting by tens, and we can see that missing bar there. And then this is the relative frequency. So here's regular frequency, here's relative frequency. It's exactly the same shape of graph. The only difference is the numbers that are on that y-axis. Here is using that class width of 5. So on the frequency distribution, it looked a little overwhelming having that many classes. On the graph, it's not that bad, but then it just really becomes more of a preference again of which graph you would prefer. So another way to display data is called a stem and leaf plot. We're going to use the digits to the left of the rightmost digit. That's kind of a weird thing to say. The digits to the left of the rightmost digit, those form the stem, and then each rightmost digit forms a leaf. So another way of saying that is the number all the way on the right is the leaf, and everything else is the stem. So in 147, your leaves must be, I don't know, must be a single digit. So 7 is the leaf, and everything else has to be the stem, no matter how many digits it is. So 14 would be the stem. So in this example, an individual is considered to be unemployed if they do not have a job but are actively seeking employment. The following data represent the unemployment rate in each of the 50 states and DC in June of 2008. So here's all of our data on this. We have 51 data points, the unemployment rates. In this data, if we want to create a stem and a leaf, if the leaf is supposed to be the rightmost digit. The leaf is going to be those decimal points, the 10th place digit. And then the stems are going to be the ones digit. So, for example, Alabama was 4.7, so the leaf is going to be 7, and the stem would be 4. So then what we do is we put all of our stems in order. You want them in numerical order, counting up on the left-hand side of a line, and then we're going to put all of our leaves over on the right-hand side that go with that number. So we would go back to the data, and as I look through this data, so I'd have my my stems drawn out, and you don't have to start at 0. You can start at whatever your smallest one was. So the smallest one was 2. So I would have that 2, 3, 4 started out. And then I'm going to fill in a 7 next to the 4 and for Alabama. And then I'm going to fill in an 8 next to the 6 for Alaska. And then an 8 next to the 4 for Arizona, etc. as I go. And eventually I'll get all of these numbers filled in here. And if you turn your head on the side, what it really kind of turns into then is a histogram, where the classes have been predetermined by what those stems are. So it really kind of turns into a histogram. It's just a histogram with numbers instead of with rectangles. We want to then reorganize the digits of the leaves in numerical order. So here, this was just, you would go through and you would jot them in kind of in the order you come to them in the table. But then to help organize the data even further, you'd want to take each of those and reorganize them. So for example, there in that 3 row, we'd want to put those 2s at the beginning, and then the 3, and then the 8s, and then the 9s. And so that's what we see in this next graph, is now all of those digits of the leaves are in order as well. So these are our steps. So again, how to choose your stem and your leaf. Your leaf can only ever be 1 digit. That's a rule. Only ever 1 digit for that leaf. And so then everything else would be the stems. You write your stems in that vertical column in increasing order, and you draw that dividing line. And then you're going to write your leaf next to each of the stems. And then once you're done with all that, then reorganize. Some students like to try to write them in order the first time around, but I think that's actually more work than to just write them out and then organize them. If the data are rather bunched, like if you're writing it out and you have tons of digits within one stem, so like those leaves that's just getting to be a really, really long row of numbers, then we might use what's called split stems. In a split stem, what we want to do is have any values that are in our first half of digits. So 0 to 4 be on one row, and then the next half of digits, so 5 to 9, would be on the next row. So then every stem gets 2 rows instead of every stem only getting 1 row. This is, again, a preference thing, kind of like choosing your classes in a histogram. It creates more bars, and like, again, if you kind of turn your head on the side, it looks like a histogram, so we can think of it that way. It's choosing to have more bars to show the distribution of the data, and it's really a preference. So one advantage of stem and leaves over histograms is when you do a stem and leaf plot, you're still seeing the shape again. If you turn your head on its side, it is essentially creating a histogram, but it also still maintains the original data. So somebody can still see what that raw data was, whereas in a histogram, all they can see is that how many data were there, but they can't actually see what the data were. So that's one advantage of a stem and leaf. A dot plot is drawn by placing each observation horizontally in increasing order and then putting a dot above it each time you observe it. So it's kind of like creating like tallies, but we just do dots instead. So this is our data about those cars again. So we did this as our very first example and made a histogram for it. A dot plot definitely works best with discrete data, because then we have distinct observations, as opposed to if it was continuous data, then we would have to create classes. So you put each of those observations of the discrete data on our x-axis there, and then you just put a dot above it for each time that value comes up. And again, it creates a histogram-ish looking thing, except it's just columns of dots instead of rectangles. So I've used the word distribution a few times. Distribution tells us about the shape of the graph and how the data is spread out. So here's some words that we can use to describe the distribution. A uniform distribution means that the frequency is evenly spread out across all of the values. So everything is about equal or level. So the histogram, all of those rectangles are at pretty much the same height, if not exactly the same height. That's a uniform distribution. Everything is just evenly spread out, same height. A bell-shaped distribution means the highest frequency is in the middle, and then it kind of curves off towards the edges. So let's see if we have, yeah, so here's a graph. So that first one is the uniform frequency, where it's just even straight across, and then the second one is the bell-shaped, where it's highest in the middle, and then it kind of curves down towards both the edges. It should be symmetric, the same on each side, roughly. It doesn't have to be perfectly, and notice in this example it's not perfectly symmetric because that 15 to 20 bar is a little bit higher than the 25 to 30 bar, but it's roughly symmetric, highest in the middle, and then goes down towards the sides. This skewing, I'll say for me, when I first learned this, I always wanted to do this backwards, but I think I have a good way to describe it now that will hopefully help you be straight on which way we do this. So if data is skewed to the right, the tail to the right is longer than the tail to the left. So what I think about for skewing is, imagine that the data was symmetric and then somebody started pulling on it. Which side did they pull? And so in that skewed right one, it looks like somebody was trying to pull some of those data points way out towards the right-hand side. Or skewed left, we're getting that longer tail over on the left-hand side. So the side where we have a longer tail is the side that we have the skewedness. So we'd want to say, this is our Old Faithful data. What kind of distribution are we seeing on this? So go ahead and think about what you think it is. Do you think it is uniform, bell-shaped, skewed to the right, or skewed to the left when you look at this graph? So I thought they were going to give us the answer on the next slide. This is kind of a tough one with just these bars. I would say that this is a skewed left piece of data or data set in this particular graph, because we do see our highest bar happening over on the right-hand side, and then we do have lower observations over on the left. So it does kind of look like maybe somebody slightly pulled it over to the left. It's kind of a difficult data set to determine from this particular graph. All right, we can't do an in-class activity because we're not in class today. So then our last type of graph that we're going to talk about is a time series graph. You've probably seen a time series graph most frequently if you think about maybe like a stock market chart. It shows over time how a value has changed. So your x-axis is going to be some sort of time. It could be months or years, whatever makes sense for the data set. And then on the y-axis, we're going to be plotting some particular value, and we're going to connect those together. So again, stock market is a place where you see a lot of these. So this is a stock market example. We have our years and the closing value in that year. So on the x-axis goes the time in years, and on the y-axis goes those closing values as a dot, and then we just connect the dots to look for any trends over time. All right, and that is all for our graphs today. Tomorrow we will learn about what can make a graph misleading, and so that we have some things to avoid. Remember that your Chapter 1 homework is due on Friday. Chapter 2 homework and quiz will be due next week on Friday. So make sure that you're working on those as well.